Alrighty. So, if you were in Calculus 3, fall of 2020, oh gosh, how long ago? 2023.
Yep.
Then there were two things that we talked about being very important in our class. As we called it, like one mission, one goal. And one mission was to glorify God. And one goal is excellence through obedience. And now we're going to add something because part of the Christian walk is not stagnating and being comfortable with basically not having to grow in Christ. So we're going to add one perspective. And that perspective is a life on low. Everybody say life on low.
Life on low.
What does that mean? There is something that I think you STEM people will appreciate. Ponder this for 1 second. You don't own yourself, okay? So American society has succeeded in lying to you and making you God in your eyes, okay? It's I, me, my, mine, my career, my job. I am busy. I am tired. I don't want to do that. Can you do it for me? All of these stuff. And as much, maybe I shouldn't have recorded this, but I'll say it anyway because I started. It's reflected in the way even our church worship song lyrics go. Can you do this for me? God, I sought you, and you answered me. And there's all of this I, me, my, mine language, even pervading the way we sing worship songs in chapel. Am I saying that makes the song bad? Absolutely not, because the Lord anoints those songs. But if we're not careful, that perspective can so infiltrate subconsciously the way we are processing us to God. And we forget that originally, that relationship was corporate, communal. It's God's salvation for a community, a family, a redemptive covenant involving the community, okay? And so we step away from our individualized kind of grasp on this and step into a corporate as a body, unified under the fact that we are all following him, okay? That's the first thing. And so, yeah, you don't own yourself. If you wanted to wake up tomorrow and start getting your heart beating and oxygen going into your body and exhaling CO2 to just live, you couldn't even do that. And so I think it's very, very arrogant of us to look at God and tell him, wow, thanks for, being the only reason that I'm physically alive. I just don't really want to give you that part of my life. It's kind of like, your life's on loan. You don't even own it. So the only logical thing to do from the STEM perspective is maybe let him have it. Because I'm sure he can do much more with it than you can. And that's not in the angle of condemnation, because that's a very, very sad thing. We've turned any sort of communal sense of conviction and labeled it as condemnation, when no. Condemnation is not going to produce fruit. Condemnation is what the enemy tries to do to you to try to keep you from repenting, okay? Well, on the flip side, if we then turn and think, no, the reminder that I don't own myself is going to bear fruit. Ergo, that can't be condemnation, that's conviction. And conviction is going to lead to suffering. And suffering is going to be what leads to being made perfect, which is the very thing that Christ did for you. Okay? So, we will go over these every single class period for the rest of the class because the reminder that you don't own yourself, your career, your prospects, even your intellect, it's not yours. If it's not yours, use it for him. How do you know? How do I know how to do that? Well, have you tried asking him? Okay. And so if we switch our perspective to asking him first what he wants, it puts a little different light on seek first the kingdom. Because what that's prescribing is, maybe we don't have a direction for surrender because we've never been told that part of that surrender is to then ask him, actually, what am I replacing my own plans with? And once he gives you that, then commit to that, then follow it, and then boom, we're glorifying him because we can obey excellently. Yeah? Cool. And then over here, kenodoxa. Everyone say kenodoxa. Empty glory. Who won the World Series in 1973? Nobody cares, nobody knows, and those people are all going to be dead in probably the next 60 years. And here's the thing. At the time, I'm sure that was their God, right? at the time, I'm sure winning that chip was basically the thing to do. I mean, you're at that status of life, okay? All these different things, your degree, any accomplishments you do. And what this doesn't mean is you don't try to do anything. Okay, so the reaction to this isn't, oh, life is meaningless. I'm now going to be a potato and do nothing with my existence. Okay, no. But you do stuff through this perspective. Because if you do give glory, the doxa, not for yourself, which is empty, but for him, then he's going to be the reason it's full. And that's going to be the reason why all of your accomplishments have meaning. It has meaning not because you did it, that's empty. It has meaning because of who you did it for. So there we go. Everyone say kenodoxa.
Kenodoxa.
Empty glory. So next time,
I got a question.
yeah?
So,
Kenodoxa.
yeah, in Ecclesiastes, when they usually say something like miss and worthless, they said I think the word is hara. Hara. What is your definition of that word?
That's a great question, and one that I know I'm not qualified to answer. So I will defer you to the theology department professors who can read it. Okay, 4.7, change of basis. The goal of this section is to develop a procedure
You have one.
for changing bases.
Is that really our goal?
Why do you question that, Tyler?
Because it's our goal to glorify God through excellent obedience.
Yeah. And part of that obedience is studying the classes that he has chosen to give to you. You know what? Oh gosh, no, I'm getting it off tangent. What blows my mind is it's just like, oh God, I'll go to the ends of the world for you. God, I'll go to the nations. I'll go on a mission trip. I'll serve you. I'll do. But I won't go to the library for you.
Amen.
But I won't turn in late assignments for you. I won't turn in my homework on time in the first place for you. I won't not slander my professors for you. I won't not complain about the work that I am literally choosing to do by being here for you. Anyway, so, example.
Come on now. Preach upon.
So
You mentioned Scotland.
actually,
Loki.
I would.
B1, B2. We'll define these explicitly in a second. I'm just setting up that we have two bases. So script B is a basis. Here's a C, not to be confused with E, although my handwriting will tell later if that actually works. Okay, C1, C2. So notice that how many vectors are in basis B? How many vectors are in basis C? Are those the same?
Yeah.
What? Okay, so what's the dimension of B?
2.
What's the dimension here?
2.
Okay, fantastic. So they share the same dimension, so that's important. Okay, if this had 3 vectors, do they have the same dimension anymore? No. So we probably can't, change the basis perspective. So that's just kind of like an implied thing that's going on. You need the same number of dimensions for the story. So these are bases. Basis is the singular. If you put an E in there, that's the plural, because English makes sense. For a vector space V, and I realized I misspoke, I made a mistake. It's not the dimension of the basis, it's the dimension of the vector space that you're spanning.
Okay.
Yeah. So V is the thing that has 2 dimensions, and that's why these both have the same number of vectors. Okay. This is a vector space. I'm lazy, so I'm just going to say ST for such that. And then here's our explicit values. B1 is going to be, I'm jumping the gun to my other example. 4 times C1 plus C2. And B2 can be expressed as minus 6C1 plus C2. So if the B coordinates for X, what does that mean again? Well, that means if I want to describe this vector using this specific basis, and if I do so, and those coordinates in that perspective are 3, 1, then what is how could I describe the same vector, but instead of using this basis, what if I want that basis perspective? Okay, so the object is the same, and these are the coordinates corresponding to this particular perspective. Now I'm going to switch the perspective. How do the coordinates adjust for that? That's what this question is asking. So that's what it means to then ask, find the c coordinates of x. Does the question statement itself make sense? What's really being asked here, right? We've been given two different bases. We know that these are in fact bases for the same exact vector space, right? And I'm told a relationship between how can I express each of the b vectors in terms of this other coordinate system. And then if I know for sure that I can use these coordinates to express this object in this lens, what happens to those coordinates? How must they adjust in order for it to accommodate this other perspective? Okay, so let's walk through this step by step. First thing is let's take our observation that what does it mean by definition for the b coordinates to be 3, 1? Well, remember that this was just basically linear combinations of those basis elements. So that's telling me I needed 3 multiples of the first basis element plus 1 multiple of the second basis element, and if there would have been more, there would have been the linear combination continues on. Okay, so then this tells me that I can think of, well, we first want to consider also, I'll leave that as some kind of like observation. So this is what our brain is thinking. This is what I'm thinking about before I move on. And then, what does it mean by definition to do the c coordinates of it? Okay, that means I want to put in here the vector x, and we just found out that this is how we can describe that vector x. So I'll take this and throw them in here. Right, 3b1 plus b2. And that's the x vector that I'm trying to represent with my c coordinates. Yes? Does that make sense? When I'm substituting, all I'm doing is I'm taking this. This must be what x is, the x vector. There's technically a slight, on a technicality, this is wrong, so I'll fix it. Really what this is insinuating is, this implies that the original vector x can be written as 3b1 plus b2. There we go. So there's a little technicality there, sorry. Okay, because that makes probably more sense how the substitution is allowed to work, because I'm basically just saying, well, that is what x is. Okay, so what does this equal? Well, I can take the constant multiples out, so I have 3 times the vector b1, but I want to view it through c coordinates, plus, and then I have my vector b2, but I want to view it through c coordinates again. And really, when you think about this, go all the way back to chapter 1 in that perspective. Whenever you have these linear combinations, we could make a matrix equation. So the matrix equation, with all the brackets, it gets a little bit funky, but really try to lock into just the fact that this is itself some sort of vector, and this all of this notation is used just to describe some vector. And a vector can be a column of a matrix. So let's use this entire vector described by the b1 described with c coordinates. That's just one vector, and it's a column. Okay, so it's the column 1, and then the second column here is b2 expressed in the c coordinates. Okay, and what did we do with the constant multiples? Well, that became the vector we then multiplied it by, right? And then let's actually see what those are. What does this mean? If I see these symbols, what does that actually mean? It says, okay, I have some vector. That vector is called b1. I want to describe that vector using the coordinates with the c perspective. And so I think, have we been given any information? Oh, that's what this is for, right? This is spelling out in the same sense of the pattern. To describe x with this basis means that it's a linear combination here of the basis vectors. It's no different. That's just some x relative to c, and so here's my vector, and these are the coordinates. So it's a 4 times the first one and a 1, ergo my coordinates are 4 and 1 with respect to c. Yes?
Is this technically like a transformation?
Yeah. We're basically transforming, in this case we have two-dimensional vectors, so you can visually think of this as we have the two-dimensional plane and we're transforming the grid lines inside the plane. Okay, what's the next column?
Negative 6.
Negative 6, right?
Yeah, how do you know that?
Because B2.
We know that because we are taking this, the vector b2, but we want specifically the c coordinates for that. And definitionally, that's precisely what's been handed to us, the coordinates with respect to c. And then I still have 3, 1. And when you multiply that out, it's 6, 4. Okay, so I'm not as interested in the multiplication part as is in understanding how to identify your coordinates. Okay, I know you can do that. I know that you probably don't know how to do this one yet. And so what does that actually tell us at the end of the day? That tells me this original vector x, if I chose to use the c coordinates, I could do it with 6 times c1 and 4 times c2. And that perspective is going to be precisely the same as if I had started with my original basis and done 3 of b1 and 1 of b2. Those will get you to the same exact location on the plane, according to those bases. So that's a very, very basic thing. Now, what we do with examples is we then think, what were some common things that could be generalizable to any type of problem like this? Because only one example is not that helpful. And it's impossible to do an infinite number of examples. So I'll identify a few things that would be really helpful. The construction of this matrix right here. Construction of this matrix, which came from essentially identifying the different coordinates for the first basis. So if I have basis 1, and then I describe it with the coordinates of basis 2, that kind of a pattern. So these two things are really important. And they are related, both, because they're equivalent, to this concept. And what is this effectively doing? It's changing my basis. The way I can think of this is, here's a vector. This vector is in B coordinates. So this vector is currently in B world. And somehow, some way, after multiplying it by this, it magically spits out something in C world. Not to be confused with C world. So this, effectively, what did this matrix do? It changed coordinates. So this is a intuitively named change of coordinates matrix. And we can be even more specific than that. From basis, starting basis B, right? Because that is the B coordinates. B to what?
C.
B to C. So, even though this is just an example, we can now construct something general. So, we can talk about this more generally, and we'll notate it like this. Now, for all of my fellow people who are dyslexic, you'll actually kind of love this, because we put the thing we're going to first. So we're stating, hey, I want my matrix to give me C coordinates. And then where is that coming from? From B.
Okay.
So do not, for the love of God, confuse that. So this wording right here corresponds directly to this notational order. That's the only weird thing about this section, is it's slightly unintuitive. Just get used to it, because it's not really that bad. But yes, don't forget that the arrow goes that way. So typically, you would think, why don't I just go B to C? I don't know. I'm just teaching what's in Pearson. Okay, that's how it goes. All right, but also, you'll find that if you do remember this notation, it makes the general algorithm really easy, because it tells you which sides to put your columns. Yeah?
I say this wrong, but if you were to do the change in coordinates from regular Cartesian to the polar coordinates, what would you think that the 3 and 1 would turn into if it was like a circle?
Well, we would have to first define what we mean for the basis of a polar transformation. But if you were able to make that definition, then I would take the columns from the first basis, describe them with coordinates in my polar basis, And that change of coordinates matrix would actually end up being, I think we do that in calculus 3 now I think about it. When we were doing those, when we were changing the differentials
Yeah.
from rectangular into polar, that's effectively what's going on. We just didn't call it this because we didn't know what any of this jargon was in Calc 3. Yeah. Okay. Good question.
So you say that the polar coordinates would more be the equation b1 to b2 to the coordinates, not the coefficient that you multiply it by.
Yeah, like see how these two equations are giving like the transformation explicitly? You would want to find an equivalent expression of it from rectangular to polar, and then you could construct it. Yeah. There's actually, the textbook does cover this way back in 1.9. There is, they spell it out. So if you're interested, check it out. Okay, let's get this theorem down. So I've got some basic B. Now instead of only 2 vectors, let's generalize it. So I can put n vectors in it. B1 to Bn. And if I have n vectors in my basis B, then if I'm going to have another basis for the same exact vector space, how many vectors should I have? Good. These the bases for V, a vector space. So how many dimensions does the vector space V have?
And
How do you know that?
because there's n
Good stuff. Then, let's see if we remember notation shorthand. What does that say?
There exists
Very good. There exists a unique n by n matrix that we call this P2C from B, such that, and then I'll put the equation over there. So if I want to describe a vector using the C coordinates, that looks like an E. Using the C coordinates, what I'm going to do is, well, what did I do? I did my change of coordinates matrix, and then I multiply it by the vectors in basis B. So I'm going to take my change of coordinates matrix and multiply it by my coordinates in B. So to send something to C, I start with B, multiply it by the B2C, and then it spits out C. Let's see, where the columns of this change of coordinates matrix are the C coordinate vectors. C coordinate vectors, because I mean, this is just really a restatement of this example. These are the C coordinate vectors of which specific vectors, guys? And B1, why is that a special one in this example? This is itself a basis vector. Yeah, so we're going to take the basis vectors of B and then represent those. So coordinate vectors in the basis of B. And then if you like math notation better than the English, here it is that. So that is, I have an explicit definition for this change of coordinates matrix, taking B to C, which is, I'm going to take my basis vectors one by one and then make sure I have their C coordinates of each basis vector. And that becomes the column of the columns for this change of coordinates. And I got all the way down to N. Okay? And this right here is the change of coordinates matrix from B to C. So relate the notation here. That's the change of coordinates matrix. Okay. Now there is something kind of goofy that I'll show you that's helpful to know. Also, when I dropped this marker on its head, it like squashed. So I gotta give you a second to.
Beat it.
There we go. Which one do you want up? This side or that side?
Neither.
You want that side up?
No, delete it.
Oh, delete this one. Okay. Now, because this actually gives us a really interesting way to talk about inverses, at least a different perspective of it. Because, think about this for a second. If I have the equation x, if I want to get that into c coordinates, then I have my change of coordinates matrix. That's going to go from b to c, and that's what I'm multiplying my b coordinate vectors by. So if I have something, and I'm using b coordinates at the moment, but I want to actually get it into c coordinates, then I'll multiply it by this guy. Now, this has to be invertible. And if it has to be invertible, that means there simply exists an inverse. So what if I multiplied both sides on the left by the inverse of my change of coordinates matrix? Right? If I can go one way, why can't I go back? So let's undo it. I'm going to do the inverse of my change of coordinates matrix, and I'm left multiplying it on both sides of the equation. So here's my c, and then I have c b inverse times p c b x b. And if I take an inverse and multiply it by itself, what do I know that always gets me? Identity, so we're basically not changing anything. So I can basically say I have x b equal to this matrix, the inverse from c to b, times x c. Yeah? Now, funny story. I have a basis that I'm trying to switch into, a matrix that's accomplishing the task for me, and the first basis. Starting basis, some sort of matrix, ending basis. That's by definition what it means to go from C to B, right? So what I've written here is really P from, wow, I really can't write B's, can I? Let's see. So I'm going to B from C, times that. Does the step from here to here make sense?
Yeah.
All that's changed is the order. So what does that allow us to conclude in general? It allows us to conclude in general that the inverse of a change of coordinates matrix is in fact as intuitive as we think. Just change it back the other direction, right? So E. Further, what does that tell us? If you find just one direction, you will always have a way to get the other direction because you just need it inverted. And then you can convert backwards so you don't get stuck in a coordinate perspective that you don't want to be stuck in. Okay, does this little side comment make sense about the inverse here? Okay, so let's do the actual algorithm because it's super easy, and it shouldn't be really too big of a surprise that the algorithm is going to completely be reminiscent of the algorithm we did for general inverses. Because what did we do for general inverses? Well, we took the matrix, we put an identity over here, and then we row reduce this over here until it's identity, and then whatever ends up getting, finagled around ends up being just the inverse matrix. Super, super similar idea. We're gonna we're gonna put the change of coordinates, and it's gonna spit out the change of coordinates in the other direction. because of the inverse idea. So this, you can kind of think about this in your mind if you want, or you can just use the algorithm as it is. Either way, it's row reduction. So pretty much every procedure for the entire chapter 4 is row reduction. And in some way, somehow, you will do row reduction. Column spaces, null spaces, row spaces, bases, change of coordinates. So do you see how when you're studying for an exam like this, you're really only mastering one skill and then 14 different perspectives. So hopefully that makes it slightly easier. It's still a high volume of definitions to learn, but you don't have to freak out that there's all different separate skills. The skill is pretty much the same thing. It's just whether or not you have internalized the definitions well enough to interpret results from that same exact skill. Okay, so here is our general procedure. This is the thing that you're going to want for your notes. Procedure. The reason I say that specifically is because this is whenever I go through and provide summaries or diagrams or whatever that is not in the textbook. So you couldn't find this in the book if you wanted to. So procedure to find a change of coordinates matrix ending up with C but starting with B. Okay. First thing you're going to want to do is figure out what your bases are. So suppose you have a basis B that has n vectors in it, and another basis that you're trying to go into, or their coordinates, also the same number of vectors, obviously. And then what we're going to do, not to use the same storyline every single time, but we're going to row reduce. So to switch from B to C, we're going to row reduce specifically. Row reduce. So here's how I'm going to build this matrix. I'm going to put the C basis vectors over here on the left side. Okay? Easy to remember because if you do your notation correctly, which one's on the left side? Okay? So that's a little bit helpful. You'll know you've done it right for that specific direction if you have it like that. And then we're going to augment it. So this is similar to the inverses algorithm. We'll augment it with, then we put the B basis vectors over here. Yes?
Setting it equal to each other.
So I always remembered this, and I still remember this by this. Because I forget which ones come first. Is it the B ones or is it the C ones that come first? The ones that come first, these are the coordinates that you want to end up in, okay? The coordinate, the perspective that you're coming from is on the right side. And then this gets reduced to, and this is the part where it's going to look a lot like your inverses algorithm, the identity matrix. We want to get these C's all the way down to the identity matrix. And then over here, that's by nature, if you could do that correctly, you will just spit out what that matrix is supposed to be. So, not difficult. I mean, quite literally, that's it. Changing bases, boom. You just need to know how to do row reduction. Yes, Denzel?
So how can you tie the bottom part of that page to the top part of that page by knowing that? Because if you just made the thingamabob, wait, I'm stupid. Never mind. You're right.
You're okay. You're not stupid. You're a math student. That's basically what it feels like. No, okay. I mean, I'm not going to lie to you, that is the entire procedure. So let's do an example and walk through one, but I mean, there's really not much to talk about.
10 by 11.
Now, here's the one thing that people are going to mess up probably, is it's going to give two different bases, and they will just simply forget the order, right? So if I'm going from B to C, visually, it looks like you're doing it with the C first, okay? So there's nothing really I can do to help teach that more clear than just heads up, don't mix that up, okay? Because there's really no saving a fundamental definitional crisis, you know? So just make sure we know that it's B to C. And the only reason that we're writing it this direction is to remind you to put the C on the left. So let's do an example with actual numbers. We'll have a basis in B1 and B2. We'll have another basis, C1 and C2. These are going to be bases for, we'll put them in the plane again for R2 with B1, let's have B1 equal to minus 9, 1. B2 equal to minus 5, minus 1. And then let's have C1 be 1 minus 4. And our second C basis vector, C2, be 3 minus 5. Okay. So let's find P, B, C. Wait, no. Let's not do that one first. Let's do the other one first. Let's do this one first. Okay, so here's our algorithm. It's not crazy. To switch from B to C, I'm going to reproduce this. So I'm going to say, okay, I want to switch from B to C. Ergo, I'm going to put my C1 here, my C2 here, and that's all. So then I augment, and then I have the basis that I'm coming from, B1, B2, over here. All good? Okay, so then, we actually have values, so let's put them in there. What's C1? Yeah, 1 minus 4. What is C2? Okay, what's on the other side of the augment? And minus 5, minus 1. Yeah?
So that means we're gonna represent C within the linear combination of B.
So that first example when you had the B basis vectors already represented as in the C coordinates, that was just to set up the definition of change coordinates. But in general now we want to think about it through this perspective, because this generalizes. So I don't require explicit descriptions of B with respect to C anymore. I could just have B's and C separate, and this is going to take care of it for me. So you don't necessarily need that information to get this done.
That one just proved.
Yeah, that one was just used for motivation, to set up that specific matrix so that we can see what matrix we're interested in. But practically speaking, when you're just given bases, you won't always be given all of those interdependence relations. So we use this.
Makes sense.
Yeah. Okay, so what do we do with this matrix? Yeah, and specifically, we're trying to get the identity on which side?
The left.
Yeah, the left side. Okay, so let's do that. Over here, I see I could take, row 2, and then I'm going to add 4 times row 1, because minus 4 plus 4 should give me my 0, and then return that to the second row. So that'll be row equivalent to, actually I'll make some space. So here's 1, 3, minus 9, minus 5. So then 0 by design, minus
7.
5 here, by quad, yep, 12 minus 5, 7.
Negative 35.
Negative 35.
And then negative 21.
Negative 21. And then I love a string of multiples of the same exact number, so let's pull that out. I could do my second row and just divide everything in the second row by 7, and then return it back to the second row. So I have 1, 3, minus 9 minus 5, 0, 1 minus 5 minus 3. Okay, and then now I just need to get rid of that 3. So I can take row 1 and subtract away 3 times the second row and return that to row 1. So I know that after performing that, I will end up with identity over here. So I know that I'll end up with identity on the left, and now let's figure out how this pans out. So here's my minus 5 on the bottom, here's my minus 3. So what happens to this entry? Well, I got the minus 9.
6.
Yeah, so you get positive 6. And then
And
what
4.
about this one?
4.
4. How do I interpret it once I've gotten my identity with respect to the number of vectors? Yeah, this is in itself, by the algorithm, supposed to spit out precisely what I was looking for. The change of coordinates matrix that takes us from B to C. So I could then answer, I could say, well, then, so what you don't want to do is you do not want to have this as your final answer. Because this technically is still a 2x4 matrix that is most definitely not a change of coordinates matrix, right? So you would want to separate out. You want to make your final answer a statement like this. P from B to C is 6 minus 5, 4 minus 3. That would be what you want to constitute your solution.
So, trying to go by the definition of, not the definition, but the thing what you did on the board that is like showing how to get there. If you had a question that was like, ooh, because we now have the P of C to B, B to C, what would the P from C to B, you get what I'm saying?
Yeah.
How would
If you wanted to go the other direction, you got 2 different options here. The first option is just start over, and instead of having the C vectors over here, they'll switch places, you'll row reduce it, and you'll reach the answer. The other thing you could do, especially if you only have a 2x2 matrix, is just slam it through the inverse formula, because you know that the inverse of that will be precisely from C to B instead of B to C. So that's a highly contextual thing, though. If this was an 18x18, ain't no way you catching me doing an inverse formula for an 18x18 matrix, right? So I would just put it back in the old tried and true. So there is no singular way to do any of this. Read context. If this were an exam question, and it were a 2x2, and you can easily generate just the inverse formula, that'd probably be the smartest thing. But it's not the only way to do it. Okay? So, real quick, how do we interpret this? Right? So let's think about all of the different things going on. What this is telling me is that if I have vectors represented with B coordinates, switching them to C is the simple computation of just multiply by this. Now we've done all the hard work. This matrix is done. So any B coordinates, I can just multiply on the right, and boom, the output will always be the exact same vector, but this time using the C coordinates. Nothing else to it. So remember when we were initially talking about this, so if I have some vector and I want it in C coordinates, I need my change of coordinates matrix from B to C, and then the vector represented with the B coordinates. We have done the hard work of finding this one. So essentially, if I want to figure out what the C coordinates are for something, with respect to this example, all I'm doing is I have my 6, minus 5, 4, and minus 3 matrix all set, primed, ready to go. And all I'm doing is I'm throwing in whatever desired b coordinates over here are. And that's it. A few definitional things. What that tells me, because I think Lang was asking earlier about like the dependence of how is the first basis linearly related to the second basis? Well, you actually have that information from each of these columns, because if you remember closely from your notes, each one of these columns originally comes from taking the first, here, like so in the first column, the first basis vector, and using the c coordinates to write it. And then this second column is the second basis vector, but with c coordinates. Yeah, because let's test that and see if that's actually true. Because we have values. So let me erase just this line here. What I'm claiming is that, like, so this coordinate matrix is that this column right here is the basis vector b1 if I were to represent it using the c coordinates. Okay? So let's expand that out. That would mean, well, we know what that is. So that's 6 minus 5. Right? So that tells me that b1 is equal to 6 times c1 minus 5 times c2. Does that make sense?
Yep.
So these are coordinates for this perspective. Is that actually true? So what is b1? What do we know b1 actually is? Negative 9, 1. 6 times what do we know c1 is? And what do we know c2 is?
3 negative 5.
Yeah. 6 times 1 is 6, and then minus 5 times 3 is negative 15. So what's 6 minus 15? Okay, so negative 9. 6 times minus 4 is minus 24, but then here I have positive 25. So what's 25 minus 24? That's how the bases are related to each other. Okay? So not only does this change your coordinates, but it's explicit column by column instructions for how to relate your first basis to the second basis. Okay? So I could similarly do B2. Actually, let's do that. So now that you've seen what I'm talking about, see if you can apply it. So let's take B2. What is the C coordinates of B2?
4 negative 3.
How do you know that, CM?
Because we found our transform matrix and in the second column, which is associated to our second vector, is 4 negative 3.
Good. Okay. Someone else then. What does this tell us about B2?
4 times c1
Plus.
plus
Or minus.
3 times c2.
Okay. So does that check out? What is B2?
B2 is negative 5 negative 4.
What is, and then so C1 again, minus 3 times C2. So we look. 4 minus 9 is what?
Negative.
Oh my goodness. Negative 16 plus 15.
That's crazy.
Okay, so that's the relationship between the very first example of this lecture and this one.
You should draw an explosion. What?
Wow.
Is it a gram?
The Matrix is attacking.
I'm so sorry to do this to you. I'll have to repent for that later. Okay. Alrighty.
You're white.
Here's does this make sense? Do you think you could do it on your own? Is it less like, is it a little bit demystified? This is not a crazy algorithm. It's quite literally, what are my basis vectors? Can I put the circle in the circle-shaped hole? Can I put the triangle in the triangle-shaped hole? Right? So put your C basis vectors on the left, That on the right, that's specifically if you're doing this direction. What happens if I want to go the other direction? What do I do over here?
Flip it.
Oh my goodness.
Do it inverse.
You will be fine.
Transpose it.
Okay? What? Ooh,
I
no.
did the inverse.
No, really, this is kind of devious.
I think I did it right.
What if instead of a basis B, it's a basis
C.
F?
Ooh.
Okay? And instead of a basis C, now hear me out now,
Z.
a basis H.
Mm.
Oh my goodness. That's actually impossible, okay? So if I wanted to go from F to H, what order would they be appearing here?
H, F.
F, the H, and the arrow pointing there. So then which basis vectors would I put on the left?
H.
Why?
F. B.
Wait, well, where does the seed go into?
Lecture is dismissed.